Right, ladies and gents, welcome to this week's Geotalk. Thank you all for joining us. It's great to be here. We've got a good audience in the room, as well as a bunch of people on Zoom and on YouTube. So thank you, everyone. And thank you to John Hancock and the CCI group for sponsoring the drinks and chips in the room. Those of you on Zoom, and our speaker, unfortunately, won't get drinks and chips, but maybe we can convince John Hancock one day to deliver drinks and chips to the entire audience. Hopefully he's not listening to that. Anyway, thank you all for joining us, and it's a real pleasure to welcome Professor Stephanie Werner to the Geotalk stage. She is joining us all the way from Oslo in Norway, where she is a professor in the Center of Earth Evolution and Dynamics, SEED, at the University of Oslo, and she's also affiliated with the Department of Geology at the University of Oslo. She got her PhD in 2005 in Germany, working on the geological evolution of Mars. And so she is eminently qualified to speak to us today about Mars and the evolution of Mars. And she also did 2 postdocs before that. And perhaps most significantly, she is the division president in the European Geosciences Union for Planetary and Solar System Science, as well as one of the lead members of the ExoMars Landing Site Selection Committee. So choosing sites to send rovers to on Mars. And I'm sure she'll speak more about that this evening. So Stephanie, thank you so much for joining us. We really do appreciate it. And we can hand over to you to share your screen.
Okay, thank you already for this long introduction. And I have to correct, I'm not any longer president. I was until 2021, but it's almost correct.
Almost.
Okay, I share my screen. Okay.
Perfect. We just
yeah. So should be now in full screen.
Yes, we can see your full screen.
Okay.
And we can hear you very loud and clear on this side.
Good, and you can see the pointer.
Yes, we can.
Okay, good. Okay, then thanks a lot for the invitation. It is unfortunate that I cannot be in person and give this talk. It would be much more fun. But now you have to listen to me through the loudspeakers and listen about Mars in a short history through time. So as a brief introduction, for those who have been mostly working on Earth, which of course is also a planet, but Mars would be the 4th planet seen from the sun, so further out than the Earth. And it's named after the Roman Greek god of war. So Mars would be the Roman name and Ares the Greek name. And I only point out Ares because you use the word geology, and equivalent would be then the word areology for studying geology on Mars. But of course, we are lazy and use the words which we know best. Anyway, we can also see Mars with the naked eye. And this is an example which uses only a binocular. And you see Mars in the center of the picture as in its typical orange color. And you can already identify this white polar cap and that there are some shades of orange across the globe. A few more numbers. So the distance from the sun is 1.5 times that of the Earth. The average radius is half. The volume is 15% of that of the Earth. The mass is 10%. So you can already estimate that Mars has not such a composition as Earth. It is lacking a large iron core. And if you want to think about the surface of Mars, in total, it is close to that what we know from Earth as landmass. It has also temperature in average -60, but that range is quite much larger than on the Earth. So we have from -40 Celsius on the South Pole to up to 35 degrees Celsius in equatorial areas in the summer on a sunny day. Picture of Mars is also shown to the right here, which is obviously not the most aggressive god of war. So I like that one very much. When we want to talk about Mars, since already 1960s, humankind has tried to travel to Mars and coming closer and getting more detailed images. But you can see that only in 64, when you look at the column to the right, the first flyby of the Mariner 4 mission was successful, bringing back photos from Mars, and we come back to that in a second. And after that, the next successful imaging mission was Mariner 6, 7, and 9. You see all the white ones in between, which are kind of not successful in either leaving Earth, arriving to Mars, or doing what they were supposed to do on Mars. And then in the 70s, 2 landing missions, orbiter and landing missions, have provided most of the knowledge which we now explore in more detail. And then we find a big gap of almost 20 years, and I will come back to that as well. But if we then go to the right, to the left column, we see that currently 11 active missions are either on the surface of Mars or orbiting around Mars, providing information. And even more missions are planned in the future. So what image did we get in 1965? And that was probably exciting for remote sensing and satellite imaging, knowing the moon already quite well. So we have the first close-up of Mars shown here. So it is not a very impressive image, but at least we have kind of the horizon across the picture, and we have something which could look like cloud. And in the second picture, we have a more clear horizon and some haze, so we can understand that Mars had an atmosphere. And not really impressive, this not so focused black and white pictures. Therefore, and that is how on the very right side, images were transmitted obviously in digital form and then printed or analogized into photo prints like these ones. But of course, one could also translate these number coded stripes, so the columns which are added into a picture like seen above here, and per hand, drawing after numbers, the first color image of Mars was made, or satellite image from Mars was made hand-drawn on paper strips. Then continuing further, so you see on the left side all the images which Mariner 4 collected. Most people were quite disappointed because Mars is bigger than the moon, and so should be much more exciting stuff like volcanism be seen or anything. But the first pictures, they showed only impact craters and nothing else. So the question or the disappointment was in the beginning that Mars maybe not worth to travel much more often there because it could be as boring as the moon. But then finally Mariner 9 brought back quite a few pictures, including this in the middle of the caldera of the largest volcano in the solar system. Also the northern polar cap here shown with ice and clouds, and then fracture patterns which have been not seen on Earth or on the moon. And as a next step of remote sensing activity, you can see in the photo down below that from these photo prints, a mosaic was made by hand by shifting the pictures in the right place to reveal one of the most sensational things which you cannot really figure out on these pictures, but maybe assume that you will have here the photo mosaic of the largest graben system in the solar system. And to make it more convincing, on the globe of Mars shown here, this graben system is spanning half of or quarter of Mars surface. And to see and estimate the dimensions, I plotted here South Africa for comparison. So it fits about 3 or 4 times in length easily into this largest graben system of the solar system. So then Mars got much more exciting and a lot of more missions were sent to Mars. So by now we have a detailed topography, and that is shown here in rainbow colors with high in red and low in blue. And the high in red, or the highest point of this map, is the Olympus Mons top with 2,000 or 21,200 meters above what we in Earth sciences would call ocean surface. And the lowermost point is minus 8,200 down here in this impact basin called Hellas. There's a few other big impact basins like Argyre and Isidis up here. The other thing which is quite obvious is that we have a split into this yellow part, the rough and highly cratered highland units, and then the smooth lower part in the northern hemisphere, and interrupted by the Elysium volcanic province made up here of 3 big volcanoes, and then the Tarsus volcanic province made up here out of at least 5 big ones and several small volcanoes. And last but not least, very prominent, the about 8-kilometer deep canyon of Wallis Marineris, named after Mariner 9, and features which are interpreted to be outflow channels which were carved by a lot of water in the past of Mars. So if we want to understand what the Martian crust is made of course we can cite meteorites which are linked to the Mars origin. One of them is the top one, Allen Hills 84001. We come back to that, and several others which are in general. This one is the Allen Hills is autopyroxenite, while most of the others are some more or less basaltic composition. And that is revealed also by near-infrared spectroscopy. So when we try to map globally on Mars, for example, the features of pyroxene, we can see in this map all this what is colored again in rainbow colors are identification of pyroxene, while in all these gray areas we have no of the signature of pyroxene found because this area is covered by dust. But this pyroxene detection, together with the knowledge of what kind of meteorite composition we have, suggests that most of the old crust on Mars is mafic igneous rocks. So also throughout time, we have collected so much information that in 2014, Tanaka and a group of colleagues made the global unified geological map, which you see here. And in simple terms, it's dividing Mars into 3 general epochs, with red is the oldest one, called Noachian. In blue colors and also greenish is the intermediate epoch, which is called Hesperian, and the yellowish colors are the youngest phase, and that is Amazonian. So the way of how these ages are defined is by the number of impact craters which you find on the surface. And when you look on the top right, then you can see that the red areas, which are clearly rough and heavily cratered highlands, have also the largest number in density of impact craters, while, for example, the most recently formed volcanic province has the least impact craters on top, and then, of course, intermediate number of craters for all the blue-colored Hesperian units. If we zoom into the Tarsus volcanic province, I told you already that Olympus Mons, shown here to the left, is the largest volcano in the solar system. It is a shield volcano with a big caldera on top. The dimensions are about 840 in north-south and 640 kilometer in east-west direction. Top height is 21 kilometer with an average slope over this region of about 5 degrees. And it is surrounded by a cliff which is still not fully understood how it formed, but it is 8 kilometers in height, and that would be 5 times about the Great Escarpment in South Africa. So this volcanic province is not only made out of Olympus Mons, which is hidden below this cloud cover, but also 4 other ones, Asia Mons, Pavonis Mons, and Ascrios Mons, and in the north, Alba Mons. Adjacent to it is Wallis Marineris again. So what is in this image seen, that we have this reddish color, and we have darker units, and then we have in white, for example, the North Polar Cap, and also cloud features. Also, when we have so many satellite observing Mars, it's only a question of time that we find the geological active proof for its geological activity. And this was a landslide. You see the cloud here covered or caught in the act. And this slope here from which it fell down is part of the walls of Wallis Marineris, shown here again, with all the black dots being landslides which have been discharged into the quite deep canyon. One example is shown here. So you see the rockfall and also the runoff of this avalanche into the canyon floor, which has nice features which are commonly well known from Earth features as well. And you have, again, topography of it and can study all these things in detail. The other thing is then to use missions to observe also geological activity, and the one after the Viking missions first which can do that with the seismometer is the InSight mission. This is a diagram of the mission. It has the seismometer in this cheese globe cover, and then a few weather station instruments and stuff further on to measure heat flow and so on. And it had also tried, which is shown here on the movie, to hammer in surface penetrator to measure under the surface heat flow and other things, which unfortunately did not penetrate, and it popped out several times and was given up to be used. I hope now the sound will work. Not like this. No, sorry. Now it should work. So you hear the measurements of the seismometer, and they extra put it in a vacuum box, which looks like this bowl, to avoid wind measurements, because what they did in the Viking missions, they put the seismometer on top of the lander, and there they only measured wind. But I think you can hear some knock sounds, which could be something else. And by now, the InSight team has measured very many earthquakes or Marsquakes, which they try to interpret if it's tectonic activity or small impact events, which trigger, of course, also seismic shaking. And if you search in internet, you can find a lot of these soundtracks, so you can listen to the sound of Mars. Okay, so then try to get back my pointer. The peculiar thing of Mars is that it has obviously an atmosphere, since we see the cloud pattern here. But the atmosphere has 96% of carbon dioxide, totally different than what we have on Earth. And the surface pressure is only 6.5 millibars, so also much, much less than what we have on Earth. But still we find clouds, obviously, especially around the big mountains. We find fog, and that is here Wallis Marineris floor, and the white stuff is all fog in the morning, which disappears through the afternoon, so you can see the floor nicely, as you have seen in previous picture where the avalanche was clearly visible. Obviously, there are several landers, like for example Phoenix lander, which had also meteorological instruments, and here is shown that the cloud coverage, which you can see, is either quite closely to the ground in about 500-meter height or in 4-kilometer heights. And this is also confirmed by images where you can see, like for example here, the hovering of the clouds quite above the topography, and in the right sun angle you see the shadow on the ground like you would see on Earth as well. This very thin atmosphere nevertheless is able to pick up a lot of dust from the surface. So you see to the left globe of Mars with its atmospheric cloud in here, and clear distinctions between different brightness of the surface. Only a few weeks later, you can still distinguish the white of the polar cap, but the difference between these two units is barely visible, and that is an indication now for that the dust which was pulled up from the surface is in the atmosphere hovering around, so that we barely can see the surface. And as this can happen, there's obviously features like this little dust devil. So the white is the dust devil and the dark is the shadow of the dust devil, which pulls dust from the surface into the atmosphere. And when the winds become stronger, you can have a cloud front of dust pulled up from the surface, as we can also observe in big dust storms from Sahara, or for example, or I guess you can find it in South Africa as well, where you have these dust clouds coming here, moving in that direction, covering up the surface features. Or further up here, you see this huge hurricane just nearby the polar cap in the north. That can be also observed through time. So we have clear seasonal variations, and this is these colorful diagrams are latitude against 3 years of weather observations on Mars. The lower one is water vapor, the middle one is water ice, and the top one is dust. And marked here are the dust seasons. So you see a lot of dust throughout all latitudes at this specific point in time, and they can be stronger or less strong. Similar, we have seen here water ice clouds in the atmosphere, and that is confirmed here by these red blobs as well. And we can also see what has been observed from distance, and for example Hubble telescope, that the North Polar Cap through time shrinks, while then in the same time the southern hemisphere get ice covered, and this works only by defrosting here, putting all of the material of volatile CO2 and water vapor in the atmosphere, settling down in the cold point. And that is happening because, similar to Earth, where we have both planets have about the same time length of a day, and also both of them have roughly the same tilt in the axis of about 25 or 23.5 degrees, meaning that we have an enhancement of the seasons in the northern hemisphere, and in the southern hemisphere during the year the planet goes around the sun. Maybe in South Africa you don't feel the seasons as much as one does it in the northern or southern hemisphere, but I can promise you we're looking always forward to the spring when the snow goes away. More clear in photographs, again, one example from the northern polar cap, here with a lot of snow cover and then without. And one of the satellites had a radar on top. So this cross section over here is the radargram then shown here, and you find these layered features in there, which is then called, very full of fantasy, layered deposits. And these layered deposits in the end turned out to be a documentation of seasonal variation, which are stronger than just seasonal variations and could be explained by something which is periodic variations relating to the tilt in the axis and the way of then when the axis gets moved further on, your deposit of ice is first of all shifted, and also you will get larger ice coverage, meaning that you have in the global dust storms less material to move around, and as a result you get in these in layers of more or less dust containing ice in the polar caps, and they have analyzed this kind of in separate beds and bundles of beds, and this is then correlated in numbers and time to what has been estimated as the obliquity variations through time. So you have here in millions of years kind of normal obliquity variations. The axis is swinging up and down, and then the axis is swinging at a specific time in different variability, meaning that you have more CO2 sequestered in the polar caps or ice deposited, and then if you change to different obliquity, you do this in a different rhythm of material deposition. So the climate change is not only visible in the polar cap ice, so-called ice cores, but we can also watch that the morphology on the surface of Mars must have been formed, or most people consider that it has been formed by water on the surface flowing. And there are several examples. So here is something which is called outflow channel. So it's carved from probably water running down a slope. If you go into more detail, you can see something which looks like meandering rivers, and then something which is the remnant of a delta deposit. And the color coding here is indicating different clay minerals which have been settled in different, with different composition in different parts of the delta. We also find this kind of what is called valley networks. So obviously something which has channel-like features, more or less meandering. So maybe they are related to flowing water on the surface. And then we have runoff, very small channels from cliffs. There are relics of which could be called islands, which are carved around empty by probably water. We have the water vapor clouds. We have the water ice on the polar caps, and we have something which is interpreted to be glaciers covered by debris, which is called rock glaciers. If we map these valley networks globally, we find them mostly in some specific areas on the highlands and also on the edge of the highland-lowland boundary. If we then fill up the entire northern lowland with water, for example, up to an imaginary shoreline of minus 2,250 meters, then we can find, especially at the edge of this kind of transition between highland and lowland, a lot of these delta. So this example is one from where we come back later to. It's landing the Perseverance rover at the moment investigating it. So it makes a lot of sense that there has been potentially an ocean in the northern hemisphere with a lot of channels which could have been carved by rain in the past. So an additional indication of that there has been a lot of water. Please remember that we have figured out that most of this old part of Mars could be mafic igneous rocks, or most likely some basalt. And when basalt comes in contact with water, it weathers and forms clays. So we have indicated by these blue triangles aluminium-rich clay minerals like smectites, micas, and carlines. And then we have in red triangles similar clays, but in this case, not aluminium rich, but iron magnesium rich smectites, but also vermiculates. Some of these areas have both colors, and some other areas have only some of the one of the iron and magnesium rich types. If we look into more detail in this region here, that is called Mars Wallis, because it's a channel here, and on the surrounding parts again indicated. So this color patch is a spectral image cube, which is interpreted to show in blue the aluminium-rich clays, and in red the iron and magnesium-rich clays. And from the morphology, you can see that the aluminium-rich clays sit on top of the iron-rich clays. When we search for this kind of combination, we find a lot of this in this Mars Wallis, but also in other places where rovers hopefully should go. This is the hopefully landing site of ExoMars in the future, and we find them distributed in several places where we have also seen that valley networks exist. And we can also determine the age by crater statistics. I come back to this, so that we kind of understand that these features are very old and have happened very early in Martian history, so that we need to think about surface weathering in a CO2-rich atmosphere. So a little more detail, because Mars Wallis is one of these perfect observational objects. So it's actually a little more complicated. So if we use this detailed spectral analysis, where we can detect in combination aluminium-rich clays, iron, magnesium-rich clays, and also carbonates, and examples of this different colors shown in the which are a combination of these three components. And obviously when it shows green, it's dominantly iron magnesium clay, for example. Then we can find, based on the spectral analysis, that we have a capping unit which is more or less basaltic. Then we have aluminium rich clays in the red zones. Then the change to additional carbonates precipitated there, transition from aluminium rich to aluminium iron and iron magnesium rich, and then iron magnesium missing the carbonates in the end. And that in traditional Earth environments may not be interpreted as a weathering front, but remembering that we have a different atmosphere. So we have, first of all, different pH value and also different PCO2 because of the CO2 atmosphere. So a typical weathering profile on Mars would have the sequence of these clay minerals abundant in its stratigraphy. And that has been before usually interpreted to be different volcanic flows which have weathered differently and not as a weathering front. So that's something new. You can produce long-term climate changes on Mars also in a laboratory, and we have done that a little bit. So you can do study and test planetary surface evolution in the lab by figuring out what you assume as atmospheric composition, and then you get some pumps and pressure gauge so that you can control the composition of the gas which is solved in the water, which then in this tank can weather the rocks in different shelves, and that is shown here. Different shelves is important because percolating through these different shelves instead of one material, you can mimic a weathering profile also in your lab. And this kind of experiments has confirmed that we would expect a weathering profile with carbonates intermingled with this kind of different clay minerals, and that they actually can produce different clay minerals as a weathering front moves forward. So the other thing what you can do is, if you don't want to do an experiment in the lab, you can study Mars actually also from Earth materials. So it is possible that when you know kind of the composition in these gray graphs from remote sensing, what you would expect on Mars, then you can go on Earth and try to find similarly looking materials to be best matching these materials which we find on the surface of Mars by remote sensing, and then figure out which of these different materials would be best resemblance of the spectral figures or signatures which we have. And that came out then for Oxyaplanum, which is the landing site for ExoMars, that we have an iron-rich vermiculite. And on Earth, this only forms in very funny places. But if you want to study vermiculite such as you have on Mars, you would be able to find it in these hollows of Granby basalt tuff, where it formed, but also some other similar things which could be analog, but not in perfect detail. If you want to see some good examples of rock collection and spectral library, you can look at our library, which is now free to access by everyone. So one thing, of course, I haven't touched upon is that geological evolution is a matter of time, and we have seen that Mars at one point may have had a big ocean and rain, but then now it is a cold and dusty desert-like thing. But when this exactly happened, we have not figured out, because I just mentioned something like 3.7 billion years ago. That is a time when Earth maybe has produced first life in quite some undefined form, and the first fossils are recorded, while actually real life, as we know it, has developed only in the last 600 million years. So whether we have a similar evolution from Earth and Mars, and we would expect some biosignatures on Mars of the same time, is still up for being solved. And the main reason why people think it is actually something which we should do is that coming back to this Ellen Hills 84001 meteorite, which was found in Antarctica 84, but laid in the shelf until 93. And only in 93, people have looked into it and found this kind of potential microfossil, carbonate globules, and polysaccharide aromatic hydrocarbons. All of these have been suggested not any longer to be signs of life, especially the PAH have been suggested to be just the fingerprints of anyone who touched the rock. But at that time, in 93 and 96, meteorites had potentially life from Mars. And as a consequence, this president of the United States decided that the only thing is to do sending rovers to Mars. And since this paper and this decision, the Martian remote sensing and rover and satellite activities has been ramped up enormously, and we are still living from this one paper in our space missions. However, whether these rovers will actually find life is another question. So if we zoom in on Mars, so far we have, so we see here a lot of successful landings in green dots, and a few also not so successful landings, with currently 4 active instruments or rovers on Mars: Curiosity, Insight, Zhurong is a Chinese one, and Perseverance. We have still not found extinct or extant life. We have no satisfactory calibration for mineral detection yet. We have actually also no control on absolute ages. We have a lot of open questions, and I didn't even touch on most, But one thing we know, there was water on Mars. So one of the main tasks, beside proving that there was water on Mars by perseverance, is to collect rocks which shall be returned back to Earth. And one of the other peculiarities is that they had a helicopter moving on the surface of Mars. It's a pathfinder to tell whether or not it is actually dangerous for the rover to move on or not. So the rover touched down here and is moving along this front of the delta to study and collect rocks. So they drill little holes and then collect the core and tube them, and then in the end another mission will pick them up from the surface. The reason why they went to this delta, you remember this very colorful image. It has quite a diversity of clay minerals, and it has also the olivine richest part of Mars seen from remote sensing on top of this plateau. The first picture was a little boring, but then later on when it turned around, it went towards, from here towards this area, where it's found then the face of the delta with some, I hope you can see that, cross bedding here and typical water produced sediment features. So why is it then so difficult to think about ages and so on? We have a lot of meteorites, and Lou Ashwell, who is in the audience, can tell you all about it, because he was one of the people who first predicted that some specific type of rocks like chagotites and knuckleites should come from Mars, but he had to wait a little until it was proven by measurements of the gas inclusions of chagotite glass of this specific meteorite with respect to Mars atmosphere, which was measured by the Viking mission. So since we now know that these rocks come from Mars, we can use them as a detailed study, and you can see that they can, like on Earth, do a lot of mineralogy and so on, study the rocks. So they are mostly basaltic with more complications. Then there are different type of rocks like these knuckleites and chessinites, which have larger grains, so they are postulated to be formed in deeper levels. One of the two other peculiar rocks is this autopyroxenite Allen Hills, which we still need to thank that all our Mars missions are happily funded by space agencies. And this one, Regulus Braccia, which contains the oldest material from Mars, as far as we know it. So the discussion now is from these rocks, we can of course determine ages in our Earth laboratories. So we see that most of these Martian meteorites are actually very young, with a few of more special age, and then the knuckleites are very sharp in time, all about 1.3 billion years old. And the chagotites can be distinguished by depleted, intermediate, and enrichment in their trace elements. And we can do a lot of other studies on when the magma source and so on has formed. So there's a review paper by Udry et al. Which give you all the detail. But one thing I want to point out is that when we look at the chagotites, and they have standard understanding for crystallization age, which range between 150 and 600 million years. And these rocks left the surface of Mars about 5 million years that you can measure by cosmic ray exposure time. When we then look and try to find where these rocks come from, we have a slight challenge. So we have our geological map. We can see young, so we want young for less than 600 million years. So we have to go to those which have very little craters. We also know that they are basaltic rocks, so we go to volcanoes. And then we have these kind of units, Tharsis, Elysium, and then there's a few others. But then if we want to, because we need something to kick them off from the surface of Mars, also want to have small craters, we are already in trouble. So we have young basaltic rocks, and this one here is not really young, but so we are limited to this one or this one region. We have actually no crater which can kick them off, because they are mostly formed, or the specific size which we need are not really fully distributed all over the globe, because they don't form so often. And then, using again spectroscopy, we can measure, of course, the spectral signature of shergotite or different of this, and Allen Hills 80 again, in the lab, and compare with what we have on the surface of Mars. And then we end up in a slight dilemma as well, because spectral features which look like our meteorites, we find only on the old part of Mars. So in agreement with the launch site, but in disagreement with all this need to be young volcanic rocks. So we have a conundrum to solve, which I leave for next generation, or hopefully for sample return, when we understand if we actually understood Martian geochemistry well enough to understand also the ages. So one thing what I will rush through a little bit now is, why is this crater statistic so important? So we use that as clock. And the simple way is that the more craters there are, the older the surface. And if we have, for example, resurfacing, then continuous bombardment tells us that the age is 2 against 5 craters in age difference. And that gives us a relative age, even if these units are far apart. To get then an absolute age, like radiogenic ages, which are from the meteorites, or wherever you want to find this kind of calibration points, we need to calibrate crater frequency against absolute age. And that has been done for the Moon, and then with some models transferred to Mars. So obviously we want to calibrate it in situ, and we have one age from Gale crater, that is here. And we have a postulate which comes from my group, that we found the source crater of shergotites, highly debated. However, if we combine the calibrated chronology model and compare between the in situ data of Farley, which have very large errors, but we actually managed to get exactly the same age by crater statistics. So you don't need to believe that, but it is one of the ways to check if we have any proper time scale to understand and watch in which epoch and in absolute ages to compare, for example, with Earth, and the rates, to derive rates we can learn from this kind of crater statistics. So that means that we could now trust a little bit more our numbers, which we put here before. So we say then that we have to move everything a little bit older, but still we have not really fully understood when exactly the transition between wet early Mars and icy current Mars occurred. So we need timescales to do a lot of things for geological processes. So I sum up now, because I guess I have flushed you with a lot of information. We have seen already these big questions that we still need to answer, but I hope I could introduce to you that Mars is actually similar to Earth, but it's not really like Earth. It's still geologically active. It had much more water before. It may have the opportunity to develop life, but maybe also not. So we have not full understanding of Mars evolution, but we have quite a lot of understanding already what can go on. We have meteorites, but they lack geological context to tell us really what is going on. we need remote sensing, or that should be also calibrated from the surface with rover missions. And if you want, you can study Mars also by experiments and analog materials which provide useful information. And with this, I thank you for your attention.
Thank you, Stephanie. Could you clap once more because you didn't hear me? Great. Stephanie, thank you so much. That was really, really fascinating. I'm sure everyone here agreed. And I'm sure there's some questions. I certainly have some, but let's see if there's anyone either on Zoom or in the room. Any questions? For those of you on Zoom, you just need to raise your hand. And then, or you can unmute, I think, and you can chat. All right, we see a question from Lou. Lou, go for it. You just need to unmute yourself.
Can you hear me now?
Now we can. Go for it.
Okie doke. So, Steph, seems to be that there's a hell of a lot of dust on Mars, a lot of storms and wind, and they're moving all this stuff all over the place. Has anyone thought to measure the composition of this dust in order to get something like the average composition of the crust? You know, they used to do this for the Earth with, I guess what they call it is loose, wind-blown sand that could be an averaging force.
Yes, they did, but don't ask me what the proportions are. So you have olivine in there, you have pyroxene in there, and other stuff. So it's, again, similar to mafic, but maybe shifting a little to not basaltic composition, but andesitic. And that is also confirmed by the more andesitic composition, which they think is in the northern lowlands.
Okay, thanks.
Right, do you have any questions in the audience here, the live audience? Yes, right at the back. You have to speak very loudly so this microphone can hear you.
Compared to Earth's geological activity, how active is Mars? We have Olympus Mars, which is huge, but it doesn't seem to be working out. So how geologically active is Mars?
Definitely, I'm not sure if you heard that question.
No, could you please repeat for me?
Yeah, I can repeat. So the question is basically, how geologically active is Mars relative to what we know from Earth, basically?
What time? Today?
Today, let's say today.
Okay, so from meteorological point of view, same active as Earth. From a geological point of view, we have quakes, let's say. We have landslides, but obviously we do not have clear evidence for volcanism or tectonic movements as much as we have on Earth's plate tectonic alike. And probably we never had plate tectonic from the beginning on Mars, but we had definitely much more volcanism in the past. So it is active, but certain ingredients are missing compared to Earth. If you take volcanism, it's probably a dormant planet by now, but meteorologically and all this interaction of atmosphere with the surface, it's fully active.
Good question. Sue, yes. You can come closer to you, no problem.
Hi, Steph. I wanted to ask on Wallis Marineris, is it possible to get an age of when it happened, a relative age from the craters in the floor? Is it wide enough? And what are the latest thoughts on how it formed?
Okay, so with features which are linear and carved into something, the danger is that you more date the area in which it forms. So you have usually only an upper age. You can do counts on the bottom of Wallis Marineris, but unfortunately there has been geological activity in the past, like, for example, the landslides which cover up features. But it is likely from the correlation of what is going on Mars that it was formed quite early together with the large volcanic activity. So it would be correlating with the beginning of the volcanic activity, and that is uncertain. So you can say probably about 3.7 billion years, maybe older, maybe younger.
Okay, great. Any other questions? Yes, Spike, you can unmute. You should be able to unmute now.
Yeah, thanks, Grant. One of the things that there are a couple of questions I want to ask. The one is apparently the frequent occurrence of peroxides in the surface of Mars. Now those are extremely oxidized, and oxidizing, we don't find them in terrestrial environments. Have you got any further information about those peroxides?
There, I think I will have to decline to answer because I'm not good in mineralogy, so I'm a little challenged here.
Okay.
I'm sorry, I guess Lou would be able to answer to you, or one of the other colleagues which do more.
I'm very sorry, Steph. I cannot help you. I wouldn't know a peroxide if it bit me in the leg.
Okay.
You could change the color of your hair, Lou.
Oh, Father Time is doing that for me.
Yeah. The other thing is those spherules, you know, the little iron oxide spherules that they've spoken about from the early rover missions. Have you any comments on those?
You mean the hematite spherules?
Yeah, the hematite spheres. Yeah. What are they?
Yeah. So I think they say that some concretions formed also due to the presence of water, but again, it's not my main research topic.
Okay, thank you.
I'm sorry.
Okay, I've got one last question. We don't want to keep you too long, Stephanie, or two questions actually. The first question, I was really fascinated about the north-south, northern hemisphere, southern hemisphere difference in ages, and I was wondering what the interpretation of that is, and if Mars is actually preserving a supercontinent frozen in time, with all the continents in the southern hemisphere and a big ocean basin in the northern hemisphere.
Yeah, so that is a little difficult to answer because the question is, since it is a topographic difference, so you have the lowlands filled up with material from the highlands. There's a lot of speculation if you can see through this cover of sediments, craters below. So it is two options, that only the surface is younger because it's filled with sediments from the highlands. Then you have a simple explanation like ocean floor filled with sediments. The other option is that you have actually some early period in time recycling of the northern hemisphere where even the crust get renewed, and therefore we have a more recent age of the entire crust. Then the other things which is in part covering up like the volcanoes in the Tharsis province and so on, that you have an enormous volcanic flooding of these areas. So that is explanation for some parts.
Okay, great. Thank you, Stephanie. That's really interesting. And then just to end off, you mentioned the future generation of scientists that can discover more about Mars. If, say, someone in South Africa is interested in getting their hands on a sample of Mars from one of the return missions, how do we go about doing that? Who can we send an email to and say, we'd like some Martian samples to analyze in our labs?
Well, we hope first that they come back to Earth. And okay. so like with meteorite collection and Apollo rock collection and so on, they are supposed to be publicly accessible by application. That means what one should prove before getting a piece of this little, very precious, because it's not big amounts, is that that your processing of this material will be according to all the requirements they have. So you have to treat it well, you should not contaminate it, you should not waste it by funny experiments or things like this. And otherwise, I think there's no restrictions to access it.
Okay, so for all the students in the room, there's a future possibility.
Yes.
To study Mars. Right, Stephanie, thank you so much. That was really informative and just amazing what we know about Mars, just from the little exploration that we have done over the decades. So thank you very much. We really appreciate it. And next week's talk is given by a PhD student from the Evolutionary Studies Institute, Sori La, who will be speaking about the origin of eukaryotes and how programmed cell death contributed to mass extinctions. So a slightly different topic, but I guess some relations to life in the solar system. Right, thanks everyone, and we'll see you next week, same time, same place. Thank you, Stephanie.
Thanks a lot. Bye-bye.